This video explain the design of the reinforced concrete columns. So the example is an elevation of part of regular rectangular frame building is shown in the figures. So that is shown here in the figures. So we are designing this rectangular columns. This is part of the frame. Below this this is between second story and third story. So you have a building here, the column continues here, and there is a above story here. So that is second story and third story. Where the columns are at 6.8 meters center each way. So the columns are sitting at 6.8 meters. From the distance between from one column to the next column is 6.8 meters. Reinforcement for the 400 millimeter by 600 millimeter column on a grid C between level 2 and T is to be designed. So the column cross section is given 400 millimeter by 600 millimeters. And we need to design this column 3. Let me put this figure here. So we need to design this column C between the grid 2 and 3. So we need to design this column C. Column C has a cross section shown in the figure. So the cross section is shown in the figure. Floor to floor height are 3.2 meters. So distance from this floor to the next floor is 3.2 meters shown in the figure. And the width of the column strip for the flat slab floor is 3.4 millimeters. So the width of the strip of the floor is 3.4 millimeters. Relative sway between the floor is not prevented. So it's an unbraced frame, meaning that under this loading this frame will not have a bracing. This joint have a translation. The design stress resultant shown have been determining from the linear elastic analysis, and column is subject to a bending only about its x-axis. Using the chart given in the figures, I think I will show that chart when we do the solution. Determining the required amount of longitudinal and transverse reinforcement, beta D is given 0.7. So let's start solve. I think these figures we're going to use it, that is given in the questions, and all these details, the moment they done the elastic analysis on this frame where they found all these design moment and load that we may going to use it in the design, and all the geometric dimensions are given here. Now let's talk about the solutions. Now the column is subjected to uniaxial bending. So uniaxial bending meaning that it has a principal axis, the bending about one of the principal axis, I think about x-axis. As it is unbraced meaning that under these loading conditions this is not restrained. The joints in here they will have a translation, so that is unbraced. Both this moment magnifier delta B and delta C we have to be evaluated. I will discuss this in the solution, how we going to find the moment magnifier delta B and delta C using the AS3600. So let's start solving. We need to first calculate the effective lengths. Okay, the effective length equations given in the standards. I will show you to that effective length equations. Now to calculate the effective length, we need to derive that factor. We need to derive the factor K that I'm going to derive here. Now taking the second moment of area of the column section as 80% of the gross sections, and second moment of area of column is calculated. So it says that if you need to calculate the moment of inertia of the columns, then you can use this table 6.2.4 in that standards, where you have a column sections. In that column sections, if you want to calculate the moment of inertia of column IC, then you have 0.8 times moment of inertia of I gross, so the gross cross section. So if I draw the column cross sections 400 by 600, that is given in the questions, 400 by 600 columns, BD cube over 12, that is the gross moment of inertia. So that is 400 times 600 cube over 12, we get these answers. Now we need to calculate this moment of inertia of IC using table 6.2.4. It says the effective section moment of inertia I effective. So I can write this I effective, let's say I effective C. Using the table 6.2.4, I can multiply 0.8 with the I gross. Let me put this is I gross. So I effective for column equal to 0.8 times I gross, and that is coming from table 6.2.4. 0.8 and substitute this I gross equal to 7200 times 10 to the power 6 multiplications gives 5760 10 to the power 6 millimeter power 4. So that is the moment of inertia of the columns. Now length of the columns is given in the examples, that you can see length of the column is given in the example 3.2 meters. That's I have written here. Now we need to calculate the beam stiffness. For that, for simplicity, I think we have two dimensions given. This width is 320 and another width is, this one is 240. So this, you can see this 320 and 240 is here. So what we can do it, we can take the average, because it is composite cross sections. We have this and then we have this depth, different depth. So rather than we can take this uniform width to have a simplicity of the calculation. So we said 320 times 240 over 2, so the average is 280. So we just, instead of taking this strip and this strip and this strip, we just take it the one constant strip 280 millimeters over the width of the column strip of 340. So we can take it 280 by 3400, and the column strip is given in the questions 3.4 meters, so it's given here. So instead of taking this beam which has a 320 280, we can make it 280 by 3400 millimeters for the beam. So now for the beam, let me talk about the fixity factors. Now if you go to the table 10.5.4, you can go back to the table here. I think I can put this mark here. In these tables, table 10.5.4, you can find the fixity factors. Now fixity factor is denoted by beta. Now we have floor slab are rigidly connected to the column at its far end. Okay, so you can see that in the frame, you can see that floor slabs are rigidly connected. So if you are talking about this beam, these columns, this end, this is near end and far end of the slab. So this near end, this far end is rigidly connected to the column end. So if it's rigidly connected, so in that case you have some options: pin, rigidly connected, and fixed. So rigidly connected, and we have another two options. We have braced frame and unbraced frame, and as I discussed in my first, we have unbraced frame. We found that it's unbraced frame. So in unbraced frame, we can take this beta value equal to 1. So beta equal to 1. Now second moment of area of the slab and beam taken as width of the column strip is 10. Alright, so I think for beam, again we need to use these tables here for the beam and columns. That's I'm going to show you here. Effective, let me put this effective B for the beam, and effective is the I effective. So if you want to calculate I effective B, you need to have this for beam and slab. It says that 0.4 times Ig given in table 6.2.4. So let's calculate the I gross. Now the I gross is 3400. I think I discussed that one. So the width is 3400 millimeters and the depth is 280 millimeters that we show in the figure, that you can take the strip, the width 3400, you can have this, then you can have this 6219.7 times 10 to the power 6 millimeter power 4. So if you substitute this value here, I think I can substitute that value here. I effective equal to 0.4 times Ig. So I can have 0.4 times 6219.7 times 10 raised to 6. If I use the calculator here, which is 0.4 times 6219.7 times 10 to the power 6 would give me the answer 2487.9 times 10 raised to 6 millimeter power 4. In the next videos, we're going to look at the we continue solving this example. Thank you.